everyone. This is my first Ruby conference, so no pressure. In 2020, Koichi Sasada introduced the Ruby community to Ractors. It's been 3 years, and we can say that the adoption hasn't been so great, right? Has any of you here used them? Okay, so I'm correct. The aim of this talk is to reintroduce us to Ractors for the purpose of driving its adoption. So my name is Abiodun, short form AB, so just call me AB. And in this talk, I'm going to take us on a journey from what is the go-to option in Ruby as it regards concurrency, to what Ractors are, why they were created, and if they're really worth trying out at all. Along with new examples and illustrations, I'm also going to be reusing 1 or 2 examples from the Ruby documentation as well as Koichi's. So let's dig in. Before we can accurately talk about Ractors, it's important that we go over concurrency and parallelism. So what is concurrency? Concurrency is the ability of a program to make progress on several tasks within the same time frame, allowing them to start, run, and complete in overlapping time periods. A good example of this would be a single chef. By single, I don't mean unmarried or not partnered, I mean one chef. So as I was saying, it would be a single chef managing multiple dishes by transitioning between them. Let's call this context switching. She could add salt to the rice at one point or butter to the cake at some other point. However, at no point is she focused on more than one dish. How then can this be fast if we're not doing everything at the same time? Well, while we are waiting for the rice to boil, we can also add the butter to the cake. And while we're trying to wait for it to simmer, we can make a salad. In Ruby, a good example of this would be threads. Context switching happens with threads due to the global interpreter lock. This is a lock that every code that has a thread has to acquire in order to be executed. What does this mean for us? It means that irrespective of the amount of cores that you have, you would only have one thread being executed at a time. Let's carry out a core usage observation for threads. These are 2 methods. Now I feel like I'm so short because I have to look up there. So I'll just look here and assume that you can see. Okay, so we have 2 methods here, a single loop one which just runs a loop, and a second one which spins up 10 threads and runs a loop. This is a brief overview of my hardware. I'm using a MacBook Pro that has 10 cores, 6 for performance and 4 for efficiency. You are the observers. You can see everything. So let's go. Keep your eyes on the cores. First things first, we run the single loop method. What happens? Keep your eyes on the cores. Suspense. Yeah, right there. We have a peak at 1 core. We kill this method and we run the thread usage method, which spins up 10 threads. Let's keep our eyes on the cores. Yeah, we can see several peaks. One's there, another one there. We should see a third one. Yes, that one there. However, we don't see all the cores busy at the same time. This might not make any sense, but I promise it will all come together when we carry out this same exercise for parallelism. So what is parallelism? In the context of the chef example, this would be parallelism. Multiple chefs handling multiple dishes at the same time. Not necessarily dancing, but you get the point. So let's carry out a core usage observation for parallelism. Single loop, as we saw before, and then now we have a new method called a Ractor usage method. It spins up 10 Ractors and runs the single loop. So keep your eyes on the cores. Remember, you are the observers and you see everything. Let's see what happens. Yes, that's what happens. All the cores busy at the same time. So I guess when we kill this, everything becomes dormant, not doing anything. Yes. So I guess this is the perfect point to ask the question, what are Ractors? According to the Ruby documentation, Ractor is designed to provide a parallel execution of Ruby without thread safety concerns. Let's divide this into two functions for the sake of this talk. The first one will be achieving parallelism. As we just saw, this means that we can have all the cores working at the same time. The second one will be eliminating thread safety concerns. What are these concerns? We have race conditions, data races, and deadlock or live lock issues. In order to understand how Ractors aim to eliminate thread safety concerns, we need to understand how they were modeled. Ractors were actually built based on the actor model. The actor model adopts the philosophy that everything is an actor, just the way we have in OOP where everything is an Thank you. Everything is an object, not a class. A class is also an object. Well, so within the actor model, we can say that the fundamental agent of computation is the actor. So I guess it's already getting pretty clear where the name Ractors came from. So from this beautiful piece of code, we can see where the name actually emanated from. I like it a lot. In the beginning, they were introduced as guilds, but with the release of Ruby 3, they were introduced as Ractors. What does this mean for us? We can say that Ractors are basically Ruby's implementation of the actor model. If you don't recall anything from this talk, remember this. So this means that the properties of Ractors are the same as that of actors, since Ractors are Ruby actors. So let's go. What are these properties? First things first, Ractors are unable to access any object through variables that are not defined within their scope. This means that any variable that you wish to access within it would have to be defined during initialization. Let's see how that works. We have an array which is going to become very famous very soon, in the next few minutes. This array has 3 items, 1, 2, 3, and we create a new Ractor within which we attempt to concatenate it. We try to mutate this array by adding 3 more items, 4, 5, 6. What happens? We get an error that says, cannot isolate a proc because it accesses outer variables array. This is because during the creation of a new Ractor, we call a method called proc.isolate. It's actually an internal Ruby method which prevents us from accessing any variable that has not been defined during initialization. How do we fix this? We can pass this array to the Ractor. Within this method, it's not really a method. Within this piece of code, we attempt to concatenate the Ractor, the array. It's actually successful. As we see, we get an output of 6 items. However, when we try to access the external array, we find something. It's actually 3 items. This is in opposition to what you would naturally expect from a Ruby method, right? So let's see. A Ruby method, we have a concat array method, and within it, we mutate this external array. When we do that, we get 6 items, and when we access this same array, we still get 6 items. That's not what happens with the Ractor. As we can see, we have 6 items, but then the array is still 3 items. So this begs the question, what array got concatenated within the Ractor? Ractors basically operate based on the concept of shareable and unshareable objects. Shareable objects are immutable, and those that are unshareable are mutable. See this like a child with a piece of candy who knows that this particular adult would always take a bite. So if you come and say, "Hello, baby, can I please see your candy?" The child is like, "Nope," because they know you can mutate it, per se. But if they trust you and they're like, "This is daddy, oh, my favorite daddy, he's not going to do anything to my candy." When you say, "Can I see your candy?" they're like, "There you go, it's shareable," right? Because you would not mutate it, basically. So see Ractors like a little child with a piece of candy. So let's go back to our infamous array of 3 items. Let's see what actually happened here. let's check the ID, and we see that we have two different IDs. One is 797420, and the other one is 824340. What actually happens is when you pass an object that is mutable to a Ractor, a deep copy is made because it's mutable. So it's not the same object. That's why we have two different object IDs. How then can we make this array shareable? We can do this by utilizing a Ractor.makeShareable method, which makes this array shareable. Remember, once it's shareable, that means it's now immutable. So within this piece of code, we make this array shareable, and we access the ID, and we try to concatenate it. What happens? We see that the ID is now the same, 824340. However, we get this error, cannot modify frozen array. That's because we have made it immutable by freezing it. Ractors basically freeze any object that you try to share using this method. So if Ractors make a deep copy of unshareable objects, and shareable objects are immutable, how then do we mutate states? With Ractors. This brings us to the second property. Ractors basically communicate via sending and receiving messages. And if they have so many, they process one at a time using FIFO. Can you see? Is it pretty clear? Okay. All right, so in here we have 4 Ractors, Ractor 1, 2, 3, and 4. Ractor 1 is the receiving one, and Ractors 2, 3, and 4 are the sending Ractors. So they are trying to communicate with the receiving Ractor, which is Ractor 1. How do they do this? First of all, they try to send. Okay, this doesn't work. Okay, yeah, you see my cursor. So Ractor 1 here is the receiving Ractor, and we have Ractors 2, 3, and 4. They send a message to the incoming port of the receiving one, and they all form a queue here. All the messages form a queue, as you can see, message 2, 3, and 4. Via Ractor.receive, the message is received, processed, and via .yield, it is sent back to the result is sent to the outgoing port. That's not okay, though, because they have to .take the result. So it's basically, I made it quite easy here. Yeah, this is easier. So we have the sending that via .send sends a message to the port, and then via .receive, it is received, it is processed, and then via .yield, the result is sent back to the outgoing port, and via .take, it goes back to the sending Ractor. The result goes back to the sending Ractor. So let's apply this to our very infamous array of 3 items. In here, we have created a new Ractor. Ractors typically terminate when the code block within them is done running. In order to keep them running, we have to put the particular part we expect to keep running in a loop. So here we have an array of 3 items, and via .receive, we receive a message, concatenate this array using this, and then we yield the result. So let's see what happens. Right now, we are going to try to use .send, .take, .receive, and .yield, push-pull type of communication. The first thing we do is we try to send an array of 2 items, 4 and 5, Ractor.send, and we call .take, and we see that we then have 5 items, 1, 2, 3, 4, 5. That array has been mutated. When we send another array of 2 items, 6 and 7, we see that it has been further mutated. So we have 7 items. What does all of this mean, basically? We're not here to discuss arrays. So what does this mean for us? It means that Ractors maintain a private state that cannot be modified by any system outside of them. So what do we gain from this? How many of you like football? Do you remember this game? Okay. So basically, we experience freedom from race conditions and data races. Without shared states, we reduce the likelihood of this because we would not have a Ractor trying to access a variable and another Ractor is trying to mutate it at the same time, typical data races. Also, we experience freedom from the overhead of using locks for synchronization. Like, basically, since they inherently prevent shared states via sending messages, therefore the traditional synchronization methods of using a mutex and locks, we would, what's the English word of trashing? Like, yeah, we don't need all of those anymore. Thirdly, we do not need to trace all state mutations to debug thread safety issues. Ractors only, the state of their state is private to them, so you cannot mutate it. So you don't, if you have any issues, you can focus on shared states. This is where it's all happening. Right here, focus our energies in one place, and we don't have to try to trace all of the places where state mutations are happening. However, it's still important to ask, are we totally thread safe? Because it looks like I've been selling gold, like, oh, Ractors are the solution to all the problems in the world. But really, are we totally thread safe? Two things. Class or module objects are shareable, but they can actually be modified. If we remember, the fact that they are shareable means they should be immutable, but they are within a Ractor program or multi-Ractor program. So it's important that if you're using this, you need to be careful to not modify class or module objects, else we introduce typical data races. Second thing, blocking operations can still occur via waiting send, waiting yield, and waiting take. So this means that we can still create programs that have deadlock or live lock issues. At the beginning, we said we have three thread safety concerns: race conditions, data races, deadlock, or live lock issues. And now we can see that it looks like we still have to tweak a few things. So the next question will be, are Ractors right for my project? We have to consider three things, maybe four. Let's see. The first thing will be speed. And in speed, we will look at computation and object creation. Let's start with computation. Is it too tiny? I hope not. This is the Tarai method, and it takes a lot of computation. This is an example from the Ruby documentation. And in here, we have a sequential version and a parallel one. The sequential one runs 4 times, and the parallel one also runs 4 times, but using Ractors. What's the result? We can see that the parallel version is almost 4 times as fast. This doesn't mean that Ractors are generally 4 times as fast, but because in here we can see that we run them 4 times, so if it was 5 times or 6 times, we would be having that same result. Let's now look at object creation. This is one of Koichi's examples. We have a method that creates objects 10 million times, not absurd at all. And then we do this 4 times sequentially and 4 times using Ractors. What's the result? We can see that the sequential version is actually faster than the parallel version. Oops, sorry to bust your bubble. Anyways, this is because Ractors share the same space, and for garbage collection, we have to stop all of them. And that's very, very costly. So you would need to identify the parts of your code that can benefit from parallel execution. However, you also need to ascertain that introducing any Ractors there are not actually slowing them down instead of speeding them up. Second thing is compatibility. Existing programs have to be redesigned to work with Ractors because many of our programs use gems, and many gems depend on global state. Ractors do not support global state because they try to maintain a private state. So if you're going to use them, you need to be sure that you are willing to take out the time to redesign your programs. The next thing we need to check is environment. When you create a new Ractor, the first thing you see is Ractor is experimental and the behavior may change in future versions of Ruby. Also, there may be implementation issues. When you see this, your first reaction is, oops, nope, on to the next. So I can understand why you wouldn't want to try them out. However, in production, you can identify non-critical parts of your code, try them out, build trust, and then expand. Nevertheless, in your test environment, Ractors can actually be greatly beneficial to speed up your tests because you can use them to actually parallelize your tests. So that way, we build trust and we still gain greatly. So this is a table, just putting everything together. Speed, computation, yes. Object creation, nope, not for now. But we are getting there. The team is working on a solution that actually isolates a Ractor such that garbage collection happens within it and you don't have to stop all Ractors. So let's hope that very soon that will be released. Secondly, compatibility, new projects, yes, because now you know how they work, so you can decide to use gems that are Ractor compatible or streamline everything you're doing towards that. For already existing projects, I would say maybe. There's no hard and fast rule here because you have to determine whether your program is actually, whether you would need to redesign it a lot or it just works based on how you've already designed your program. Environment, test environment, yes. Parallelize your tests, make them faster. Vladimir will agree. I hope I got your name right. But in production, start at non-critical points, build trust, and then expand. Now that we have seen the good, let's start, the great, the good, the bad, and maybe the ugly of Ractors, let's circle back to what they are. Ractors are a parallel execution feature in Ruby inspired by the actor model, in which each Ractor operates independently, helping mitigate thread safety concerns. We may not have all our thread safety concerns eliminated yet, and our journey towards optimal speed across all operations might still be ongoing. However, if we all come together to use Ractors and actively contribute feedback, we can enhance its functionality. We can also create more gems that are Ractor compatible, and we can create a thriving ecosystem. Picture a parallel execution feature in Ruby that is not only lightweight, it is economical in its usage of memory. It is streamlined in terms of communication complexity. You don't have to use locks anymore, message passing. And then it's thread safe. That's a feature that we can all be proud of. So let's start now, maybe not now since we are here, maybe tomorrow morning. Let's start to use them so that in the next few years, when we talk about parallelism in Ruby, it can be a party of Ractors everywhere. Thank you so much for listening. You can connect with me.